The Laplace transform operation is a linear operator. That means that the Laplace transform of the sum of two functions is equal to the sum of their respective Laplace transforms. Let's use this superposition property and the Euler formula for the cosine to find the Laplace transform of the cosine of omega t. Throughout our textbook, we use j to indicate the square root of -1. Pause the video here and try this one yourself on paper. You should make use of the Laplace transform of the exponential decay that we found earlier. Alright, did you really pause the video? If not, pause it here, get a pencil and paper, and work this one out for yourself. Substituting the Euler formula in for the cosine, and then exploiting the superposition property, we can break this up into the Laplace transform of two different exponentials. Then, using the result on slide 2, we can find the Laplace transforms of each of these exponentials. I don't know about you, but I'm not a big fan of having complex numbers in the denominators of fractions. So the complex numbers can be eliminated by multiplying the numerator and denominator of each of these fractions by the complex conjugate of the denominator. Multiplying the numerator and denominator by the respective complex conjugates enables us to put these two terms over the same denominator, s squared plus omega squared. And now we have an s plus j omega plus s minus j omega in the numerator, which is just 2s, and the 2 cancels with the 1/2 out front. So the Laplace transform of the cosine is s over s squared plus omega squared. You can use a very similar process to find the Laplace transform of the sine function. Okay, what about this one? Let's take the Laplace transform of t e to the minus at, which is a ramp multiplied by an exponential decay. For this one, again, we're going to combine the exponentials e to the minus at and e to the minus st so that we get e to the minus a plus s t. Then we're going to use integration by parts. I'll assign u equals t and dv equals this part, e to the minus ast dt. Then we differentiate u to find du equals dt, and we integrate dv to find v is equal to minus 1 over s plus a e to the minus s plus at. Now we use the integration by parts formula to find that the integral is u times v minus the integral of v du. Remember that we have to evaluate both of these terms over the domain from 0 to infinity. The uv product term here ends up being 0 when we substitute in t equals infinity and t equals 0. So we're left with just this integral. And we find that the Laplace transform of t e to the minus at is 1 over s plus a squared. One more important example function, we'll look at the impulse with an area of a. The impulse is the Dirac delta function. The Dirac delta function has an area of 1, a height of infinity, and a width of 0. You may remember that the Dirac delta function is the derivative of the unit step function. We can model the Dirac delta function as a pulse of height 1 over tw in the limit as tw approaches 0. And then, using the result from the rectangular pulse function from earlier, we simply take the limit as tw goes to 0 of a over tws times 1 minus e to the minus tws. The limit of this function as tw goes to 0 is undefined because we have tw in the denominator. So to find this limit, we need to apply L'Hopital's rule. That is, we differentiate the numerator and denominator by tw. When we take the limit as tw goes to 0, we find that the Laplace transform of the impulse of area A is equal to A. Why is all of this Laplace transform stuff useful? Well, it's fun and easy, but that's not why we do it. In fact, we usually don't bother finding Laplace transforms at all. We just look them up in a table. For example, table 3.1 on pages 40 and 41 of Seaborg. If you have a hard copy of our textbook, I would recommend that you open to page 40 and 41 of the Seaborg text and bend the binding backwards so that the binding is broken there. That way, when you toss your textbook down onto the table, it'll just flop open to pages 40 and 41. If you're using an electronic copy of our textbook, like a PDF, take a snapshot of that table and set it as the background on your laptop computer. You're going to be making frequent reference to tables 40 and 41. I think you'll find when you inspect that table that it's more comprehensive than the table of Laplace transforms that you'll find maybe in the back of your differential equations textbook. Table 3.1 on pages 40 and 41 of the Seaborg text is extremely important. Laplace transforms are useful because they help us to find solutions to differential equations. We'll remind you of how you can solve ODEs using Laplace transforms in the next video.